Okay, welcome everyone. Today we're very happy to have Dyer from Google, who's agreed to give us a talk on neural networks. This will be a part one of a two-part talk, which I'm not sure how coordinated it is, but they will both be on aspects of neural networks and machine learning and so on. As usual, after the talk, we'll take a short break, and people who want to stick around for discussions, we can have that discussion. And without further ado, Ethan, take it away.
Great. Thanks a lot for inviting me to speak. Happy tax day, everybody. So I cannot see people while I'm presenting, so please feel free to just interrupt me to ask questions. I'm super happy to be interrupted. Yeah, if anything's not clear, yeah, just go ahead and interrupt. I'm going to be talking about the effect of scale and deep neural networks. And the second half of this talk will mostly be about some work that was done with these people down here: Yasmin Bahiri, Jared Kaplan, Jae-Hoon Lee, and Utkarsh Sharma. And they're all part of the larger physics diaspora. So maybe to start, I'll just give a very narrow lightning review of deep learning. So deep neural networks at their core are just a convenient, highly expressive set of function approximators. And the simplest example just consists of a nested series of linear maps, WZ plus B, and nonlinearities sigma. By tuning the weights and biases, W and B, this can approximate a huge range of functions. So say you want to learn to classify, cats and dogs, just parameterize things this way and learn your weights. Say you want to translate text, just parameterize this thing and learn your weights. And the number of compositions here is called the depth of the neural network, while the dimension of these linear maps is called the width. And this picture on the right is a picture of Rosenblatt, who's building a physical neural network. So each cell in this grid actually represents a component of one of these weight matrices encoded through a variable resistor. And the optimization is done with a little motor that tunes the value of that weight, which is not how we're doing things these days. Great. Okay, so just to be concrete, we can consider a one hidden layer neural network, which is just a linear map followed by a nonlinearity, followed by another linear map. And a typical nonlinearity is a rectified linear unit, which is just a linear function on positive inputs and 0 on negative inputs. By tuning the weight, we can generate piecewise linear function, and the number of piecewise linear regions is set by the dimension of this weight. And so deeper networks and wider networks are able to be more expressive. And this basic paradigm, when scaled up to sufficiently expressive networks and trained on enough data, can be remarkably powerful. So some examples include image classification. This approach underlies most of modern machine translation. It's useful in medical diagnostics. It can get state-of-the-art game playing. And more recently, maybe in the last 2 years or so, there's really been a paradigm shift from what's called supervised learning to unsupervised learning. So it used to be the case, let's say I wanted to learn how to classify dogs versus muffins. I would collect a large set of training examples which are labeled as dog or muffin, and then I would train my function approximator on those labeled examples. And what has really started to take over is a different approach, which is I first collect a much larger unlabeled set of data, and I train it on some objective which is not directly related to the problem that I care about. So for instance, here, maybe I'm training my model to predict mixing pixels when I mask out some region of an image, or it could be mask out some words in text and try to predict the missing word. And then only at the very end collect a smaller amount of labeled data and fine tune the network on the desired task. And this is this shift has been important because it's much easier to collect large quantities of unlabeled data. Labeling, requires human, is costly, and so as we're thinking about scaling these networks up, this shift to this unsupervised technique working has really unlocked whole new possibilities in terms of scaling. Great. So this basic idea that one can do better by making neural networks bigger has been a central thread in the field for many years. So here's a plot just showing a correlation between the number of parameters in models and performance on ImageNet, which is a 1,000-way image classification task. And we see that scale correlates reasonably well with performance. More recently, researchers have been systematically studying the connection between performance and scale. And so here's an example of performance versus compute cost for large language models. And we see that there's, over many orders of magnitude, there's something which looks like power law scaling for the performance as a function of the amount of compute spent.
Can I ask a question?
Yeah, sure.
Yeah, I was going to ask you whether this general results known about trading off between depth and width of the net. Like, can a very deep network you can always build a very wide network equally as powerful as a very deep network, for example?
Yeah, so maybe I can try to answer that in two ways. So there's definitely theorems known about what functions are possible to be expressed. There's universal function approximation, even for that like one hidden layer network that I gave. If you take it wide enough, in principle, you can approximate any functions. But then I think that there's a more practical question, which is like, if I'm training these networks in a standard way, I don't have some magic tool to find the right weights, like which is better? Does depth buy me more? Does width buy me more? And that has been studied in various contexts, and there's not a universal answer. To some degree, there's, like, as I'll focus on scaling, there's some evidence that actually, at least within some ranges, the aspect ratio is not too important, and it's actually the total number of parameters that affects how these things are scaling. But yeah, you can find setups where both, it seems like depth is buying you more and where width is buying you more.
Thanks.
Yeah, thank you.
Can I ask a general question, just out of curiosity? These biggest models,
yeah,
like the typical time it takes to train them.
Yeah, so these big text models that I'm talking about, a couple weeks can be typical for training. And that's, yeah. Great. So, okay, so I just flashed a curve in terms of this loss, but you can also measure how performance is improving in downstream tasks maybe you actually care about. So here's a plot showing aggregate performance on various text tasks from GPT-3, which is a large text model. And here we're looking at tasks like question answering, summarization, sentiment analysis, and we see that, like, similar to the loss improvement, we get accuracy improvements over many orders of magnitude. And if you thought that this trend continued to hold for an additional 4 orders of magnitude, then these models would be achieving human or superhuman performance across a wide variety of test tasks.
Can I ask a question?
Yeah.
So in these, normally, if I'm using some number of parameters to fit a data set, I tend to worry that if I include too many parameters, then optimization only weakly determines the number of parameters. So how is it that with 10 to the 10 or more parameters,
Yeah.
Your optimization is converging quickly.
Yeah. So I mean, let me say a few things. One thing is so that the training set here is huge. So like these models are trained on like all of the internet. So when you say that, so I'm, just to make sure I'm understanding your question, one problem is like if I had a finite training set size, if I increase my parameters too much, maybe I wouldn't have enough, learning signal to effectively be optimizing those parameters. But here you're also including the amount of training data. There's, I think historically there'd been some concern that like neural networks would be hard to optimize, non-convex, maybe optimization would get stuck. It turns out that hasn't been true, and I'll have some to say about that theoretically in a little bit. And yeah, if you're not happy, I would definitely encourage you to ask again.
Okay, thanks.
Yeah. Okay, so right, so with these like coarse metrics, aggregate accuracy or loss, you can also just look at these models and see that they're developing non-trivial skills with scale. So some examples from that large text model GPT-3, it's able to generate news articles which are nearly indistinguishable to non-expert readers from real news articles. It can generate command line. You ask it, I would like to, move my cat image to the desktop. It can tell you how to do this with no fine tuning. Here's an example where, measuring these models' performance on translation task between the International Phonetic Alphabet and English. And it seems like, for many orders of magnitude and scale, it's not really doing well. And then all of a sudden it starts to do quite well on this task. Right, so these performance gains with scale lead to a lot of questions. Can we model and extrapolate how performance will change with scale? What problems are solved just by scaling up? And that points the way to what problems do we need, genuinely new ideas to solve. And then there could also, oh, sorry, was there a question? No. Oh. And then, there could be aspects of the model that are actually getting worse with scale. And then let's say, you decide, okay, like, scaling is the key, or there's design questions about how can we practically scale models up, make them bigger. So, right, so just to give an outline of where I'm going, so just completed the introduction. So I'm gonna sort of walk through some thinking about performance with scale, and I'll start with a discrepancy between a lot of existing theory on how models are thought to improve with scale and what we see empirically. Then I'll walk through 4 different scaling regimes, which I'll categorize into two types: variance limited and resolution limited scaling. Then I'll describe a solvable model that exhibits all of these scaling regimes, and then I'll close with a shameless plug. But maybe before I proceed, are there any more questions? Okay. Right. So this question of how performance depends on model size is a classic question in learning theory, and there's sort of a textbook answer that you may learn, which is, as I start with a not very expressive model, at first I underfit data. And then as I add more parameters, I start to be able to fit my data well. And then if I add too many parameters, maybe I go through all of the training data points, but I don't generalize well to unseen new data, and I overfit. So that would suggest a picture where as I take my model and I increase the number of parameters, at first the test error goes down and then it goes back up. But that's not what we see in practice when training deep neural networks. What we see is essentially no performance degradation as models are getting bigger and bigger. And this is known as generalization paradox. And one route to getting some insight into this paradox is a dramatic simplification that occurs for wide neural networks. So forgetting about deep networks for a minute, just remind everybody what it means to use a linear model for prediction. So a linear model, which is not necessarily a linear function, is just a linear superposition of potentially nonlinear features, f mu of x, weighted by some weights theta. And if we're, say, trying to optimize so that this linear model is predicting some target y, maybe we use something like a quadratic loss. And this becomes quite simple system, because the weights theta appear quadratically. We just have a quadratic convex optimization problem. In contrast, if we have a network given by a deep neural net, in general, this can be like a highly non-convex, complex optimization problem. But one of the remarkable insights in recent years has been that as we take neural networks to be wider and wider, the infinite width network actually approaches a linear model. So the dynamics become much simpler as the network becomes wider and wider. And in particular, this also helps shed light on why there's no, there's asymptotically no optimization problem in these wide networks. And one route to derive this simplification is via a Tuft expansion, where here, what plays the role of the large N matrices is the N by N weight matrices in our neural network. So, one can introduce a double line notation and compute expectations of our neural network over the weight initialization, but one can also push this through and use it to compute finite time training dynamics. For instance, one can compute the evolution of the output of a network around infinite width systematically in an expansion in 1 over width. And so here plotting in blue is the empirical output of a finite width 128 neural network trained on MNIST, which is a 10-digit classification task. And this is the difference between the empirical network's output and the linear predictions. And so, the strictly infinite width linear prediction would be this solid line just at 0. And the dashed line is, gives you a 1 over width correction. And in principle, this machinery can be cranked and one can compute higher and higher order corrections to the wide network evolution.
Ethan, can you explain what this theoretical prediction is? I didn't understand. What is this model that you're talking about? What is the 1 over n expansion? Can you give us some more details?
Sure. Yeah. So so here, you have in this explicit example, but you can be more general. But in this example, you have a 2-layer network. So 2 hidden layer networks. So that just means 2 of these. So 3 linear maps and 2 nonlinearities, where the dimension of that, the linear map is mapping you from some input. In this case, it's MNIST digit classification. So you take an image, you apply a linear transformation, you apply a tanh, you apply a linear transformation, you apply a tanh, and then you map that with another linear transformation to numbers between 1 and 10, 0 and 9, I guess. And then you train this via gradient descent. So just to try and match the true label. So that's like, that's just the trying to train a finite width neural network to predict digits. And then what you can compare that to is, let's say, so at infinite width, that training procedure becomes equivalent to training a linear model where the features of that linear model are the derivative of your neural network map with respect to the weights. And you have those features frozen. and you're just optimizing a linear model. And so the solid black line is, I mean, here I'm plotting the difference between that strictly linear evolution and the evolution of this full neural network. I am happy to go through the full details if you'd like after, but all I'm saying is that so these neural networks are initialized with weights typically drawn Gaussian random at initialization, and so you can compute expectations over that initial weight distribution throughout training. And you can use this diagrammatic expansion to compute the moments of that over that initial weight distribution. But then because that then is evolved forward in time, you can actually compute the expectation throughout all training and use it to see that at leading order and large width, a lot of potential nonlinearities that you might worry about are actually suppressed. And then systematically incorporate those. And so here in this plot, the dashed line is not just taking the leading linear part, but taking what one gets by computing including the 1 over width terms as well, but then dropping, again, an infinite series of higher order terms. So right, okay. So one can if one has this expansion for the network output in terms of the width, one can push this through and see how the loss should scale in terms of the width of this network. Just Taylor expanding the loss gives us that we have some infinite width limiting behavior of the loss plus a 1 over width correction. And here below is an example of that in here. This is CFAR classification task, which is a 10-way classification of animals and trucks and cars. And the pink and blue lines are looking at particular times during training and seeing that the finite width loss indeed approaches the infinite width loss by something that looks like this 1 over width prediction. Great. So this 1 over width prediction for the scaling of the loss is a recent result for deep networks, but it actually has a familiar flavor to other generalization bounds found in the literature. So in particular, it's common to find mean field-esque bounds where the loss is predicted to scale like 1 over d or 1 over root d, where d is the dataset size. In terms of the data set, and 1 over p or 1 over square root p, i.e. 1 over width, where p is the number of parameters. And the point I'm making here is that these are data independent power laws that are typically integral or half integral. And if we compare that to what we see in practice, so here's examples of what we see when we just actually scale up networks and measure how their performance improves with dataset size or parameter count. We get something which looks quite different. So on the left is an example in this, again, ImageNet 1000-way image classification task. Here the blue line is the curve for the loss, and we're seeing something which scales like dataset size to the minus 0.35. And on the right is an example from large language models where we see exponents that are very different from those mean field type exponents. And so there's this qualitative discrepancy. So here's an example of one of these classic generalization bounds exhibiting these sort of mean field-esque exponents. There's a discrepancy between that theory and what we see in practice.
Other than saying that the powers are integer or half integer, is there any connection to mean field theory?
Yeah. I mean, as I'll explain in a minute, there's a one can, the route to deriving sort of all of these predictions is does come from like I mean, a Gaussian approximation, but no, I guess maybe not anything beyond that. It's not like yeah.
For the Tuft expansion that you showed us, have people tried doing like a padded resummation or something with a few powers? Like take the next few leading terms and do a resummation to see if it actually converges?
Yeah. Not to my knowledge. Yeah, I don't know of such work. And I'll emphasize in a bit. Well, this I mean, I think it's intellectually interesting to ask that question, but as I'll emphasize in a bit, actually, this scaling with width of these over-parameterized models in some way is not really the question you'd like to answer. And the reason for that is, if I think about training a large network, so here, if I have a network with many more parameters than data points, its performance is not limited by the capacity of the network. In that case, it's limited by the size of the data set. And so, it turns out that this, the thing that has this nice perturbative expansion is this dependence on the quantity, which is not the quantity that's primarily affecting performance. So, more interesting is, say, the data set scaling for these over-parameterized models than the model size scaling. Okay, so the next portion of this talk is going to be a tour of these 4 different scaling regimes, namely the scaling with dataset size for under-parameterized models and over-parameterized models, and the scaling with model size for under-parameterized and over-parameterized models. And to start off with, I'll discuss this the scaling with data set of under-parameterized models and model size of over-parameterized models. There's actually a sort of a quite simple argument that underlies, I'd say most of the theoretical work on how these models are supposed to generalize, and it's just the following, which is that if I imagine some random variable a, which concentrates around its mean a bar, and I have variance and higher moments suppressed, then if I look at some smooth enough function of this variable, I can expand this, and it's going to be concentrated around the function of the mean with corrections controlled by the higher moments. And one very simple way to get such a thing is if my random variable is a mean over many independent draws of some underlying variable, then I get higher moments by central limit theorem, just corrected, just controlled by 1 over the number of terms in the sum. And so this large width limit that I briefly described earlier is an example of this, where we have that the network output concentrates around this infinite width behavior with corrections that scale like 1 over width, and so we get these variance dominated corrections for the loss. And one can work out a similar scaling in under-parameterized models with respect to data set size where the the corrections around an infinite training set are just given by 1 over d fluctuations. All right. So we can go and measure this in these limits, and indeed we find that the dataset size scaling for underparameterized models and the model size scaling for overparameterized models is consistent with these predicted scaling behaviors coming just thinking about the variance of our estimates. Right, but as I mentioned, this is not what's seen in practice when looking at on how models scale. And so to understand the scaling behavior, to understand the scaling behavior observed in practice, we need to focus on these other regimes. And just to say again, the regimes you expect the scaling to be most interesting is exactly these dataset scalings for overparameterized models and model size scalings for underparameterized, because then you're scaling with respect to the quantity that is limiting the performance.
So can I ask a quick question? Is this still depth, or is this width, or what is the scaling?
Yeah, so so this whole plot, the parameter scaling is just accomplished by scaling width. In these plots of parameter scaling, it's scaled by a combination of depth and width. So the variance limited argument, I can formalize, say, for just the scaling with width, and I don't know how to formalize it if I scale both depth and width. But I think I expect something like that to hold if any kind of combined depth width limit has a well-defined limiting behavior. I'll explain a solvable model in a little bit where it's the total number of parameters, but that's a linear model, so it's that's maybe not so clear. Okay, so so how can we get some intuition for this resolution limited scaling? The picture that I'll describe is as follows. So imagine we have data which is drawn independently from some smooth d-dimensional manifold, and that the target is a smooth enough function on that manifold. Let's imagine that what the network learns to do is something like for each new test point that it's seeing. So like here, I'm imagining the training points are depicted by these blue circles, and the test point is this maroon circle. Maybe for this new test point, it just uses its closest training point to make the prediction. So that's like, so here little f is the learn function, and fancy f is the actual smooth target function. So we're imagining the prediction is just given by the prediction on the closest training point, which is learned perfectly. If that's the case, then so for instance, for this maroon point, this would be the closest point. So if that's the case, then we can understand how the loss would scale in that setting. And just expanding the test prediction around the neighboring training point, we get some leading quadratic behavior. And if we want to know how this scales in expectation, then the question is just how does the distance between nearest neighbors of points sampled independently scale if I have a data set of size D. So D nearest neighbors sampled independently from a smooth manifold. And there, the distance just scales as D to the -2 over the dimension of that manifold. So as I add more data points, the nearest neighbor distances become smaller, but if I considered a larger dimension manifold, then it converges more slowly. And so just to emphasize, this type of scaling behavior is now somewhat non-trivial, depending on the dimension of the data manifold. Well, first off, it depends on the dimension of the data manifold. So it's a data dependent scaling behavior, and it can certainly be non-integer. Okay. Now, similarly, we can imagine a similar setup if we think about how underparameterized models scale with the number of parameters. So now we're imagining, we have the number of training data points much larger than anything else in discussion. So rather than data drawn from a smooth dimensional manifold, we can just imagine that that's what the data is. And adding more capacity, our network is just learning to better and better approximate this manifold. So for instance, if we imagine, ReLU networks, then we just have some piecewise linear approximation to a smooth d-dimensional manifold. And if we think that the number of regions is scaling with the number of parameters in our model, then again, we get something which scales with a non-trivial exponent governed by the dimension of this manifold, with the integer constant depending on whether we're able to just match the value of our function or match its first derivatives. Okay, so again, we can go and look, and indeed in realistic models we find that in these regions we have data set dependent exponents which are non-integer or half integer.
Ethan, it looks a bit like dimensional analysis, where you're just converting volumes to lengths.
You're saying getting this nearest neighbor scaling?
Well, just the 1 over D. It looks like you're just converting some volumes to lengths.
That's all it is.
But so, are there critical exponents in these in this phenomena that are beyond those kind of dimensional analysis formulas? Like, are there scalings that don't follow from that?
Yeah, what to say? I would say, like, we don't fully understand, all the details of scaling, but as far as I know, this seems like, a fairly reasonable picture, and no exciting, like, non-perturbative effects or even, like, perturbative corrections to exponents or anything like that seem like they're needed. Yes, sometimes this type of scaling, this 1 over D scaling is referred to as, like, cursive dimensionality scaling. I don't know if this is a word that makes you happy or not, but it's essentially just that if you want to if you want to fit a function in high dimensions, you pay this 1 over D penalty, and totally you can get this factor just converting lengths to volume. Say, like, you have a lattice that you're trying to approximate or something like that.
So even if I went beyond the Gaussian approximation, you don't expect that I'd get some corrections to that sort of scaling? Yeah.
So, I mean, I think, I mean, maybe, yeah. So combining a few of these questions, right? There's like this, you could try to study. So I've sort of talked about two limits. One is like the, these variance limited exponents. And then I've talked about these resolution limited exponents. And you could ask like, how do you connect the two? And at the moment, I don't have any good answer. You could imagine that there's some resummation on the perturbative side that you could do, and maybe like, and maybe connect these. I mean, I think that would be very interesting. I just don't have any great ideas on whether that's doable.
But empirically, you have the data connecting them, right? You could draw a plot.
What plot are you imagining?
I'm just imagining, the same sort of training, but on, scaling simultaneously the number of the width or the data size so that you get into the intermediate regime.
Yeah, so you can plot all the way through. You have like, you don't have scaling, like for instance, let's say I fix my data set size and I start with a model which is small, and I just increase the number of parameters. What I see is, and let's say I train to convergence, what I see is like a region which looks roughly power law with this interesting exponent. Then I see a breakdown in this power law behavior. So I see, this is sometimes called the double descent curve, but I see something which looks like a decrease, a bump, and then a decrease again. And the first decrease is given by, I don't know if you can see me on the screen, but this first decrease is given by this interesting power law. The second decrease is given by this uninteresting, or whatever, this perturbative power law, and the intermediate region is not given by power law scaling. And then there's what I'm describing is sort of focusing in on the asymptotic power law on these two sides, but it doesn't, shed any light on how to draw this intermediate curve.
But is the intermediate curve the one that one would aim for in practice in a real model, or you don't want your model to be either underfit or overfit?
No. So the I think the optimal training is typically to live in that first power law region. So the living at this intermediate point.
So just to clarify, the first power law region corresponds to which? To having fewer parameters than like kind of underfit, or?
So yeah, sorry, maybe I'll say this different. What you'd like is to critically scale up both so that you're not wasting, you're sort of maximally taking advantage of compute. So like, you can keep scaling up your model, but you get diminishing returns if you have less data. You can keep scaling up your data, but if your model doesn't have the capacity, you have diminishing returns. So what you'd like is to scale up both. Mm-hmm. If you'd like, so if you do this, what we'd like to be able to understand is like, what's the power law that's describing scaling up both? And that seems to be smoothly connected to the power law that you get on this first side of the plot, which wasn't scaling both. It was fixing, say fixing data set size and say looking at the model scaling. So the exponent that you get on increasing model size when you're under parameterized seems to be like smoothly connected to this interesting exponent of scaling up both.
Why is that?
So one picture, yeah, so that's a good question. I think like one picture, if you think about these manifold approximation pictures that I'm describing, you could imagine that like in, so there that like as I'm scaling up data or model size, I'm approximating the same underlying data distribution. And so then, I can go to either side. Either I like completely smooth out this manifold and I'm just approximating it better and better, or I'm sampling data points from this manifold, and I have this near neighbor distances. But if it's the same underlying manifold, then then these predict the same scaling exponents. And you can, So I'll maybe it'll become slightly clearer in this solvable model that I'll talk about in a minute. But then I'm happy to keep talking about it. All right. So yeah, let me walk through this solvable model. Sort of inspired by the fact that these wide networks reduced to linear models, and also just because it seems like a lot of features that sort of are originally thought of as being special to deep neural networks can actually be realized in linear models. So we can actually see all 4 of these scaling regimes in the following model. So we have a bunch of nonlinear features, capital Fm of x. And we have our target, which is sometimes called a teacher network, is just built out of a linear superposition of these features. And then the model that we're training, our student, is a linear superposition also of fixed nonlinear features, which are some subset of some randomly chosen subset of the teacher features. As I mentioned, since this is a linear problem, we can just exactly optimize and compute the loss at that optimum for this teacher-student setup. And we have something that's totally determined by the so-called kernel. That's the average of the 2-point function of these teacher features over all features. Here, this kernel K, if the decorations on top of it indicate that sometimes we're evaluating this on the training set, and sometimes we're taking the expectation over the whole data distribution. If these 2 things were the same, then our loss would just be 0. But the reason we get non-trivial dependence on dataset size comes from the fact that sometimes we're evaluating on just the training data.
Sorry, what was K with 1 argument versus 2 arguments?
So right, so the over bar, so K is a function of arbitrary points, but we can take those points to be on the training set. Yeah. So like K with this arrow and a single argument is 1 arbitrary point, 1 training set point. The bar is 2 training set points, and then this is again 1 training set point. Is that clear?
Yeah.
Cool. Right. Okay. So what we'd like to do, right, is not just have some expression in terms of these kernels, but we'd like to understand the scaling properties of this loss. To get some insight for, so to make progress, we're going to have to make some ansatz for what these kernels look like. But we can just look at them on some realistic data to try to get a sense for what's a reasonable ansatz. And so here's an example of the kernel spectrum evaluated on here. This is MNIST, so again this 10-digit classification task, but pooled at various scales. And we see that we get kernels which might suggest an ansatz of some power law type ansatz for the spectrum. And if we make that ansatz, then we can compute the behavior of this loss. So it can be computed using replica trick, or even more simply, if we make a further assumption that this exponent is large, then the eigenvectors of the d-top eigenvectors of this empirical finite kernel align with the eigenmodes of the full kernel, and we get something which just projects onto the tail of the spectrum, and so scales as dimension to the minus alpha k. So just in pictures, if we go ahead and assume some power law scaling for our kernel spectrum, then that implies a power law scaling with respect to data set. And one can run a similar argument with respect to model size for the loss scaling. Okay, and so
can you go back to the plot with the numbers?
This guy?
Yeah. So I mean, what is the dimension of the data set? Should we be comparing to a number over D? Alpha K is some number over D. So what's D?
Right. So that's a good question. So the input dimension is MNIST, so it's just 28 times 28, but that's I would say not the relevant dimension. And I think so we can discuss what the dimension is later. But for instance, if I look at MNIST and I look at like the PCA decomposition of MNIST, it has much fewer number of important principal components than 28 squared. It has a much smaller effective dimension. So how to precisely characterize what the data manifold that this data is represented smoothly on is a good question. And one way to do it is like, for instance, in this context where you're training a neural network on the data, is that if I think about, again, we can use this nearest neighbor distribution to estimate what the underlying data dimension really is. And so then you get a connection between this estimate of the data dimension using this nearest neighbor distribution and the predicted loss scaling. But making that precise is, I think is a good question and something that don't fully understand. This doesn't address your question about what precisely is D, but one thing to observe about what's happening with this kernel spectrum here, following this power law behavior, is that so far I just said like this is a good ansatz because look, the data kind of looks like that, but we actually know that smooth kernels have power law bounded spectrum. So this is work that goes back to Weil, and so depending on what smoothness assumptions we assume about the kernel that we're considering, then we get a different bound on how the eigenvalues should decay. And furthermore, for sort of generic smooth kernels, we expect that they saturate this bound. So instead of motivating this ansatz from an observation of the data, you can also imagine that what we're seeing is just that these kernels are sort of saturating this smoothness bound.
There's some like differential operator on this manifold whose spectrum you're computing.
This is this kernel. It's like an integral operator. Yeah, it's
an integral. Okay.
But this, yeah. Okay, and so one can go ahead and look in this linear case empirically here again for pooled MNIST, and observe all of these advertised scaling regimes. Right. Okay. So in conclusion, there are these. Hope I've convinced you, at least empirically, that there are these four regimes which have qualitatively different exponents, and this resolution limited scaling has more interesting exponents, potentially with geometric origin, and is more relevant for practice, and that kernel models realize a solvable version of this. But there's many open questions. What controls this data manifold that the model, the model has learned, and what's the best way to actually measure this manifold and determine D. Can we make architectural changes that actually improve these exponents, for instance, say decreasing the dimension that the model is representing data on? Before finishing, I want to sort of switch gears entirely and mention for the moment theory-free practical way of getting a handle on how things are, how large text models are improving with scale, which is that we're organizing a new data set to test the limits of large language models. And so this is an open call for tests. If you or anybody wants to, has some burning question and you'd like to know how big text models answer this question, you can submit your task, and it will be evaluated on models ranging from a few million to hundreds of billions of parameters by OpenAI and Google. And there's already been 90 tasks submitted. Some tasks we already see pretty impressive results for these models with scale. Other tasks, it seems like the models are not improving, but I would encourage people, if they have a task that they think is hard, please submit it, especially because sort of, tasks that aren't improving with scale seem like important places to look for what is missing in our current thinking about large models. When we say these models are doing bad, it can sometimes be hard to tell. So here's an example of a question that got submitted. The question was, what's the human organ that pumps blood? And this is what the model spit out, which got marked as wrong. But then if you go and look at what that's encoding, it actually ends up being this beating heart emoji. We asked, ask the model to repeat the dog 4 times, and the word dog 4 times, and the model, the model takes this literally, which gets marked as wrong, and just says the word dog. We also get, there is an empty fruit basket, then 1 fig is added, then 1 plum is added, then 1 date is added, then 1 plum is removed, then 1 fig is removed, then which fruits are in the basket. And the model was trained on the internet, so it says that this question gets 71 views. And a related question is, 2 boys can finish a piece of work in 12 days, while 3 boys can finish it in 8 days. How long will 1 boy take to finish that work? And it suggests that would get 1,577 views instead. Just one last anecdote. Often there's a task which was submitted, which tries to get the model to translate things into Pig Latin, and often the model just responds with "ukfe ofye." So, anyways, can be hard to judge when models are wrong or right, but they definitely do some interesting things. And so, if you're interested, physics questions are welcome. Deadline is June 1st to submit a task. You'd be included, on a paper with this benchmark, and your tasks will be evaluated across a whole range of scales. So,
what is an example of a physics question that is reasonable to ask?
You can ask any question that you can think of. If it's and all of them are reasonable, I would say. It might not be interesting. Some.
We're asking if it has common knowledge of certain physics questions, certain common knowledge physics topics.
So, common knowledge is one thing, or reasoning is maybe more interesting. People have asked, what's heavier? What would happen if, you threw a ball, and there was no gravity? But then people also ask mathematical operator related questions. There's LaTeX typesetting questions, which is probably not that interesting physics, but I mean, I think I'd say what's not interesting is, say, like memorizing, like, if there's a bunch of common physics questions that exist on lots of web pages, these models are decent at like remembering what they've read on the internet. So just asking those questions again, unless you had some design to target memorization, might not be interesting. But I know Jesse Taylor asked if it could write a plausible paper with a CC problem solution. And it started talking about minimally coupled scalar fields, and like, anyways, it doesn't seem noticeably that much worse than, a lot of papers purporting to solve the problem. But maybe that's a hard metric to actually evaluate on. So I would say, like, really no limits aside from your creativity. It might be that like we don't get any signal on your question for many years if it's too hard or something like that. Okay, so yeah, thank you.
Thanks, Ethan. Does anybody have any quick questions before we take a break?
I had one quick question. I remember a graph fairly early on where basically performance wasn't improving at all.
Yeah.
And then all of a sudden it started improving.
Yeah.
There's some notion of like phase transitions that are sort of understood, or...
Yeah, again, I think that's a great question. So there's a bunch of these examples which have like if you look at the loss, it's just sort of monotonically improving. It doesn't look like there's like exciting dynamics there. But if you go and look at one of these tasks, sometimes they look the same, or sometimes they look like, I mean, I can put it back up, but there's many examples like this, where you see nothing, and then all of a sudden it seems like it's understood how to do some concept. So yeah, here this translation task. I don't think we just don't understand this very well. Like, it could be something like the metrics that we're using to evaluate are too discontinuous. Like an example of this is like accuracy, although that's not so bad. But you might be improving in loss, and then you only see an accuracy jump once you get over that threshold where you're actually classifying things correctly. So maybe these are all just, if we had the right soft metric, we would see a continuous improvement. But we don't have it, or it could be that there's some non-trivial dynamics. And yeah, I think that's a great question.
All right, thanks, Ethan.